This is one of the most classic optimization problems. Usually when you start doing optimization, you start with this type of problem. So which pair of sides maximize the area of the rectangle? You might already know the answer. It's another shape, which I will not say what it is right now. But what I will do right now is I'll write some equations and see what we need to do. So we need to maximize the area. First thing we should do is we should write down what the area is going to be. So the area is going to be S1 times S2. But then this is a little bit problematic because now A depends on the input of S1 and S2. So we need two inputs. And so this is like differentiating in two variables, which is something we've not encountered yet. But there's a fact which we still have not utilized. It tells us that the parameter of this whole thing is 4L. So that's good. So 4L is the parameter. But can we write this parameter in terms of the sides of this rectangle? And the answer is yes. So it's twice of S1 plus S2. Then that's amazing because I can find the relation now between S1 and S2, and then maybe I can reduce my two variables to one variable. This goes away, becomes 2L. So 2L is equal to S1 minus S2. Let me write S2 is going to be equal to 2 minus S1. I just solved for solved for S2. And then that's amazing because now I have using the constraint, I was able to reduce my two variable function into a one variable function, and you will see why this is true in one moment. So this is an area which depends only on one side. So this will give us S1 times S2. But then you're like, hey, why are you writing S2 again? I thought this was a function in one variable. But then this is easy to argue against because we have this relation between the two. I don't want to say variables, but variables. And so we have a function in one variable, which we need to minimize. Now, to minimize this, we need to do two things. We need to find the derivative of S1 and then find the x which make the derivative of the area equal to 0. That's how we optimize. So the first thing we can do here is we can find the derivative of S1. This is a function, sorry, the derivative of A. This is a function in S1, so we can differentiate with respect to S1. So if you distribute and take the derivative, you will get 2 minus 2S1. Because you get 2S1 minus S1 squared, if you're wondering what's happening here. So you take the derivative of this, you get this, take the derivative of that, you get that. Okay, and then the next step would be to set this to be equal to 0 and find x. Well, S1 in that case. You want to find S1s. That will make your derivative be equal to 0. And this is not too difficult to see now. You just need the S1 to be equal to 1. Now, if you want to check that this will be a minima, you can take the second derivative. And so the second derivative will be negative. It will be minus 2. And if the second derivative is negative, at this point S1, it's actually negative. So it's negative 2 everywhere. But if it's negative 2 at S1 is equal to 1, then this should be a maxima. Did I say minimize? Okay, this is a mistake from my side. So you need to maximize. If the second derivative of S1 is less than 0, then S1 is a maxima. This fact utilizes the construction we had with the oscillating circle. This is one of the facts we just used now. Could also do the following. So we found an extrema and we are trying to figure out whether it's a maxima and a minima. Actually, we know it's a maxima from here, but I'm showing you two different ways you can check that it's a maxima. So if this is S1, it's equal to 1. You can plug in, for example, 0, then you get something that's positive. And if you plug in, let's say, 3, you get something that's negative. And so what's happening here is that you have your function, it's growing. Let's say it's going up, and then it starts going down. Then this point must be a maxima. So there are two ways again to check that this is a maxima. It's either using this this fact or that fact. You plug in some values and you do some analysis, and then you make your nice conclusions. Okay, so this is we're almost there, because we want the side lengths. So if S1 yes, it has to be straight. So if S1 is equal to 1, then S2 is equal to 2 minus S1. So it's equal to 2 minus 1. I think 2 minus 1 is equal to 1. So our pair is 1 and 1. And in that case, it's actually a square, which maximizes the area of the rectangle. This is what I was hinting at in the beginning. So this is the answer to the rectangle area optimization problem. It's a classic. And from here you can also deduce that the maximum product of two numbers which have a given sum is this sum divided by 2. Then you take the square of the number. So if you have, let's say, two numbers that sum up to 10, and you want to maximize x times y, then you would take x to be equal to 5 and y is equal to 5. You can do this in your mind. So maybe try 6 and 4, you get 24. Try, 7 and 3, you get 21. But then indeed 5 and 5 is the right combination. The squares are the ones that maximize. Now this is not a part of the exercise here. I'm just giving you more and more and more intuition. And hopefully I was successful in doing this.